Okay, hello there again. Now what we're doing is continuing on from the last problem. Now instead of rotating it around the x-axis as we did before to produce that frustrum, that sort of truncated cone, by rotating a trapezium around the x-axis, now what we're doing is we're rotating the line around the y-axis. Now these are the big ideas. These are the big ideas when it comes to rotating a line around the y-axis. Firstly, you're going to have to make x the subject of your equation. Secondly, you're going to need to adjust your limits. Boys, you can see that when we rotated around the x-axis, our limits were from x equals 4 to 0. But wait a minute. When we're rotating around the y-axis, our limits now change from 9 down to 1. From 9 down to 1. And that's because when x is 4, y is 9. When x is 0, y is 1. So we've got to adjust our limits and we've got to make x the subject of our equation. But apart from that, the procedure is the same. So, making x the subject of our equation is reasonably straightforward. We're going to end up with 2x equals y minus 1. Therefore, x equals y minus 1 on 2. You might think of that as this is very slow today, x equals y on 2 minus a half. Okay? So we made x the subject of our equation. The other thing to do, as I said, was to change our limits. But apart from that, it's very similar. So what we're going to do is this. We're going to say the volume is equal to pi. Our new limits are 9 and 1. And this is what we've got to square. Y on 2 minus a half, all squared. And we are integrating in respect of y now. Okay? That's the first time I think we've done an integral where it hasn't been dx on the end. Okay, so what's that going to give us? Well, now here we could really use the sort of chain rule to great effect. I didn't use it the last time because I said that's not the usual procedure, but it might just be a bit easier here, so let's see how it goes. So the volume is equal to pi, what we're doing here is we're going to put this in brackets, y on 2 minus a half. What we do is we raise the index by 1, divide by the new index, and then you'll remember that the final step is to times the denominator by the derivative of what's in brackets. Remember, this only works for what we entitle linear factors, where the highest power of the variable, in this case y, is 1. So it is here. Anyway, the derivative of that is a half. Okay? And then that is our integration done, which was fairly painless, I think you'll agree. 9 and 1. Okay, let's tidy that up a touch. So we're going to say that's equal to pi, and we still need our square brackets there. We've got, let's just think ahead a bit. 3 times a half is 3 on 2. Now when we divide something by a fraction, we tip over that fraction and multiply. So what I'm saying is that 3 on 2 is going to become 2/3. Okay? So we will write this as 2 on 3, and then let's simplify this a bit. Common denominator, so I can write everything in terms of a half. 3, 9 on 1. Okay, so let's substitute away. We're going to end up with some big numbers, so I might allow you to evaluate that. But we can take it further by saying, let's substitute 9 in. We've got 2/3 9 take 1 is 8. 8 divided by 2 is 4, and 4 cubed is 64. So, like that, let's get this in some rounded brackets, and then we're going to substitute 1 in, let me just check that, 9 take 1 is 8, 8 divided by 4 is 2, 2 cubed, 4 cubed is 64, that's correct. Okay, minus, substitute 1 in, 2/3, like so, running out of room here. 1 take 1 is 0, that's nice, because that's going to give us a 0 there, and we're going to cube 0 to still end up with 0, and that's going to be, come to 0. So that's nice. Okay, so what do we end up with here? Pi, 64 times 2 is 128 on 3, and therefore the volume is equal to 128 pi on 3 units cubed. And there we have it, rotating a line about the y-axis, producing a volume, or a solid with a volume of 128 pi on 3 units cubed. And that's where we might leave it. Nick? Thank you.